for the individual slope for MLR, you're testing a null hypothesis is beta I equal to 0, just one particular slope. Okay, that's going to be a t distribution. Right? The degrees of freedom are equal to just the degrees of freedom for the error, n minus k minus 1. Comes from the error. Okay. If you're ever not sure, if you're doing simple linear or multiple linear regression, you don't know what degrees of freedom to use for your t distribution, it's always just the error degrees of freedom. Because the t distribution only has one degree of freedom. Okay? The f distribution has the numerator and the denominator degrees of freedom. Okay, so that gets us through regression. And then we've got the one factor ANOVA F test. Okay, so one factor ANOVA F test. We're going to have an ANOVA table again for that one. Okay, so our source is going to be the different treatments, the error, and the total. The degrees of freedom are going to be, we've got k different treatments, whatever that is. I've got n minus 1, n is the total sample size. And the error just makes up the balance. Right? I never remember, I have no idea ever what the error degrees of freedom are. I don't know any of those error degrees of freedom formulas off the top of my head. I always just have to write out the ANOVA table. Okay? So that's a one factor ANOVA F test. We've got, after that, two factor ANOVA. No interactions. Oh, and so our distribution here is an F distribution with k and n minus k minus 1 degrees of freedom for one factor. Okay, two factor ANOVA, no interactions. We've got our sources, our factor A, factor B, okay, error, and the total. Okay. And now you have to be careful because you get two different F statistics when you're dealing with two-factor ANOVA. Okay, you've got multiple hypotheses to deal with. Okay, your factor A is going to have degrees of freedom I minus 1. Okay, it's the number of levels of factor A. B is going to be the same thing, but for the number of levels of factor B. The total is going to be still same thing, total sample size. So in a balanced design, it's going to be ijk minus 1. Okay, that's total sample size right there. Okay, and the error just makes up the difference. So this is ijk minus I minus j plus 1. What that works out to be. Sure. So that's two-factor ANOVA, no interactions. We get two different F distributions right here. You get I minus 1 times whatever the error degrees of freedom are. And then J minus 1, the error degrees of freedom as well.
The error degrees of freedom would be the same in both cases, right?
Yes, it would be exactly, yeah, the error degrees of freedom is the same. That's just going to be that formula right there. Right? Which, yeah, come on.
For single factor, no, but you have the degree of freedom written down as k minus 1.
Oh, you're right. You're right. I apologize. That is k minus 1. Thank you for correcting me on that. Yeah, I was thinking on back to multiple regression. Number of treatments minus 1. Yes?
What's the difference between the capital N and the lowercase n?
So usually I use lowercase n, or usually we use capital N when we've got like a big multi-factor experiment or something like that, or a 1-factor or 2-factor experiment. So this is like the total sample size across an ANOVA. Whereas lowercase n, I've used that in 1-factor ANOVA when we're talking about replicates occasionally. I don't have that notation anywhere in here. I've just used lowercase n really in settings where we're dealing with regression and 1 sample, 2 sample testing, that sort of thing. Okay? So really capital N is just like total sample size in ANOVA stuff. Okay? Okay, so we got 2-factor ANOVA, no interactions, and then finally the last test is 2-factor ANOVA with interactions. Okay, so you've got A, B, the interaction between A and B, and the error, and the total. Okay, total's the same, ijk minus 1. A, still I minus 1. B, still j minus 1. You can figure out the interaction, it's just the product of the two of them, which makes some sense. Okay, and the error is like whatever remains from this. Okay, so this is, I forget what the formula is for this. I would just calculate it by adding up these 3 and removing it from the total. Total degrees of freedom minus rest of degrees of freedom. And then you're going to get 3 different F distributions that you're going to worry about here. You're going to have the I minus 1 error degrees of freedom. You're going to have the j minus 1 error degrees of freedom. And then I minus 1 times j minus 1 error degrees of freedom. So that covers all the hypothesis tests we've done, I guess, aside from the 3 chi-squared hypothesis tests, which we already talked about. So maybe going through and making sure you're familiar with all the mechanics of those different hypothesis tests, remembering the assumptions, how plots look for each of those would be good. Yeah, yeah.
Can you go over the difference again between the F test for overall effect and ANOVA for linear regression?
For what?
The F test for overall effect for a linear regression versus the ANOVA table?
So you mean an ANOVA table within? So you mean like a 1-factor and 2-factor ANOVA versus regression?
Yeah.
Yeah. Okay. Sure. So what is the difference? So difference between F test for overall effect for regression and 1 and 2-factor ANOVA. Okay, so regression deals with, okay, both of them are going to have quantitative response variables. Okay, so you're going to look at your response variables, they're going to be some sort of quantitative continuous value. Okay, both regression and ANOVA. Okay, but when you look at the explanatory values, for regression, they're mostly going to be quantitative, and then we talked about using indicators to deal with categorical explanatory values. Okay, so with indicators. Okay, but when we're dealing with ANOVA, we only deal with categorical explanatory variables, right? So think about, we had, you know, in the fertilizer case, looking at plant height, okay, we had just 3 different treatments. There isn't some sort of quantitative, I'm not, you know, I can't plug A, B, and C by themselves into some kind of equation. If maybe I looked at a linear model where I included the amount of fertilizer together with an indicator for A, B, or C, then I could do regression, okay? If I had some kind of quantitative explanatory variable in addition to this categorical one. But when I'm dealing with solely categorical variables, I've got to be doing ANOVA. Okay? Does that make things clear? Cool. Yeah, Tim?
Between the simple or linear regression t-test and f-test, isn't the f-test superior? So when would we use the t-test?
Okay. So it turns out that they're both totally equivalent to one another, right? So Tim's pointing out that you have, when we're dealing with simple linear regression, okay, you have an f-test and a t-test. Okay? The p-values are the same for each. Okay? They are totally equivalent to one another. One is not superior to the other. When we're dealing with simple linear regression, they both are addressing the same question, testing whether or not this slope is statistically significant. Does it differ from 0? So we talked about both of these. Really, I could have made a choice to just teach one of these two, but I wanted to be able to look to both of them when we moved on to multiple linear regression. Because when we're dealing with multiple linear regression, now they differ from one another. When I'm talking about multiple linear regression, the f-test is a test for the overall effect of the model. So it's testing, is your model overall any good? It looks at all of the variables together, beta 1, beta 2, all the way through beta k equals 0. But when we're talking about a t-test, which you might think as being more powerful, but it doesn't give us really specific information about any of our variables. The benefit of the t-test is I can look at individual slopes. Okay? T-test is for individual slopes. So maybe my model, I'm looking at what the crime rate is based on all sorts of values, poverty and single-parent household rate, urbanization, education, high school literacy rate, all sorts of things. Okay, and maybe my model looks great. I reject the null hypothesis for the f-test, but that doesn't really tell me, did I really need to have the single-parent household rate in there? Okay, so the t-test says, okay, look at that individual slope. This is testing, is beta 3 equal to 0? Okay, and that determines, does that particular explanatory variable contribute, the third one, and contribute to the explanatory power of the model? Okay, does that make sense?
How do we know when you're asking for a confidence versus a prediction?
Sure. Yeah, confidence versus prediction intervals. Okay, so prediction intervals are always for randomly sampled individuals, or really for individuals. Usually randomly sampled ones. Okay. So sometimes the way that I write the problems, it doesn't necessarily follow this sort of randomly sampled pattern, but it's for one individual in particular. So I know that my brother is 6'2", okay? I'm trying to predict how tall is his son specifically going to be. Okay? That's going to be a prediction interval. If I want to know how tall, on average, do men whose fathers are 6'2" grow to be, I want to know something about the population mean. Okay, so the confidence interval tells me something for population mean. Okay, I'm not just predicting what my brother's son's height's going to be. Okay, I want to know what the average height for all men whose fathers are 6'2". Okay, so two things to look for here when you're in the problem where it asks you about the confidence interval. Check, am I talking about one person specifically? Or, does it mention something about a population? Okay, does it mention something about an average or a mean? Okay, that's probably indicative of a confidence interval. But if it's just one individual, I'm not averaging anything or anything like that, I'm going to use prediction. Okay? You got it? Okay. Sounds good. We got 7 more minutes, so I'll hang around, but if you guys want to talk to me individually.
How long is it compared to the other tests?
So I still need to edit it, but the goal completion time is like 2 hours and 15 minutes. So yeah, 2 hours to 2 hours and 15 minutes, so it should be shorter, like for the time period that we've got.
All the tests, we're gonna ask things that each session. Are you gonna specify for us to tell us first?
Yeah, I won't ask you to when I say, give me a summary of your results or something like that. I'm not going to ask you to compare 5 different means and list every specific pairing or whatever. It's probably more likely that I give you someone's interpretation of your results, and you've got to say, is this interpretation correct? Rather than having to write. I never like you guys to have to write paragraphs. I much prefer that you read paragraphs than write paragraphs. I have not seen this. So on the first exam, they had.
It's only going to be.
I think
It
it
won't
was
be like a full
25 energy between the two or whatever. So not a very large difference. And then for the second exam, there's basically no difference.
Okay. Cool, thank you.
How many explanatory variables you've got? Okay. So yeah, so simple linear regression just means you got one explanatory variable. I'm looking at what is my height is my father's height. Okay, whereas multiple linear regression, I'm going to include my father's height, my father's shoe size, my mother's height, all sorts of other explanatory variables. Yeah, indicators. Yeah, we could never have indicators in simple linear regression. We can only get one explanatory variable, and if it's simple, it's got to be quantitative. Okay. What's that?
There's no
Okay.
way
The experimental error. Okay, so the way that you should think about this is just right? When I'm looking at, let's say I give you guys some kind of treatment, okay, before the exam. Today, I give like half the class coffee or caffeine or something like that, okay? And maybe that's gonna have an effect on exam scores, maybe it's not, okay? So that effect would be the treatment. But there are gonna be a bunch of people that all receive the same treatment, right? How many classes are gonna get no caffeine, okay? But their results differ. And we say that that difference is experimental error. When I have replicates, right? I've got a bunch of individuals that I treat as replicates. I treat as they're receiving the same treatment, but they can be different.
If I get 100,
I have to say that that is experimental error. So it's just any,
with the extra.
difference in the
If I get
response
102,
variable that isn't due to the treatment, that happens
If I get like
internally
95,
within.
then I'll get an A-.
Does that make sense?
So I just get a good figure.
So you have
Mm-hmm.
22 and a half.
So internal variability, so this is one potential source of experimental error, and that's just like you and your, right, so it's sort of contrast with the rest of it. So inherent variability would be like you and someone else who received the same treatment do different on the exam because you are different people, right? You're, someone else or whatever, you just have different knowledge of the material, you study different amounts, okay? That's an example of inherent variability. That differs from something like measurement error. Measurement error would be like, I'm grading your exam, okay? And I just like miscalculate the points. Or maybe I just like grade you wrong or something like that. But the way that I'm actually making the measurement, that's the source of experimental error. Whereas this is like something that's fundamental to you, to my experimental units, the difference between my replicates. Measurement error is something that like, if I am careful about things maybe, then I can reduce measurement error. With inherent variability, I gotta change something about my sampling design, my experimental design, to reduce it. Inherent variability in experimental units, okay? Alright, that makes sense?
So a couple weeks ago, you said that they misgraded number 2 on the exam and it has not been updated since. I want to know, should I
Oh,
post the regrade or?
shoot, oh, okay. Man, I think I updated it for another section and I forgot to update it for this section. So I do need to update that. Yeah. Okay.
There's one little difference in the interpretation for the t-test earlier, and then the test with the simple regression.
They have the same exact interpretation. For simple linear regression, yeah, they have the exact same interpretation.
So this is like the significant.
Oh, I just, there were some of the solutions for the review.
Okay.
Okay, the one was the case 9,
Yeah, from the last
Yes.
semester.
and then the other was on exam 2 solutions.
Yeah. Relationship, right? For T1 equals 0. For an overlay.
Okay, so quiz 9. Okay. Which part?
On number 6.
5, 6.
Okay, why did we do like this to figure out how much gas is needed instead of
Um,
like the max is less than 2 times the.
Yeah, this has to do with. It's basically the way that the solution is written is just in terms of the variances, which are the square of the standard deviations, instead of the standard deviations themselves. So since it's squared, you're looking at there's less than 4 times the difference. But this you're correct in how you should approach this or whatever.
Okay.
Is just look at the smallest double that, see if it's less than the biggest, and that is the case there, so almost get S. So, you're right. Okay?
And then the other one was exam two.
Okay. Three B, okay, that is, so what about,
Keep going down.
oh, I'm looking at exam one, that's the problem. Okay, so this one.
Okay, there was one we had to circle, oh, this one, okay. Is that supposed to be there is sufficient
Oh,
evidence?
you're right, that
Okay.
is, yeah.
Okay, got it.
Alright, I'll add that.
Thank you.
Mm-hmm.